We know this guy. If you want to differentiate 4 to the power of x, you get the natural log of 4 to the power of x. There's another guy I'm going to tell you the derivative of. I could prove it, but we've got time issues. Do you know if you want to differentiate not the natural log? We know what the natural log is. I guess I should put the natural log here for completeness sake. If you want to differentiate the natural log, your derivative is 1 over x. If you want to differentiate the log to base 10 or the log to base 3, do you notice that the difference is that you still have a 1 over x, but you have this funny 1 over the log of 3. Now you see when it's a power like 4 to the x, the extra bit, the log, is multiplied. But when it's a log of a different base, you see that the natural log is divided. You see the difference between them? Right, so it's not the same. When it's 4 to the x, it's multiplied. When it's log to base 4 or whatever, it's divided. These are the 3 new guys, and then we'll start our next section. And these ones I'm going to do as pure magic. I'm not going to attempt to prove it, but you could. And I'll show you very roughly how I would prove it. But the inverse sine function. Remember from 142, the inverse of both sides, it's actually a function. And its derivative, you're just going to trust me, is that ugly guy. And the inverse cosine is rather strange. It's almost exactly the same thing. And the inverse tan is that guy. So you're just going to add this one and these 3 to your list of things you now know how to differentiate. I'll assume that you've already got these 2 guys in your list. So we've pretty much got every function that you're likely to need to differentiate. We've got them all now. Right, we can, oops, that's not what I did there. We can differentiate x cubed. And we can differentiate square roots. We can differentiate using product and quotient rules and chain rules, tons of functions. And we can differentiate 4 to the x, log to base 4, natural log, inverse sine, cosine, tan, all 6 trig functions. I mean, it's a pretty decent sized list if you wrote them all down. So what I'm going to do now is just some practice at differentiating some inverse trig functions. And it's going to be the same kind of situations you'd expect. Product rule, quotient rule, chain rule. Let's start off with differentiating that guy. I hope you would recognize that as a product rule, agreed? 2 things multiplied, x and an inverse sine of x. And if you want its derivative then, it's f dash g plus f of g dashed. And you differentiate this guy, you got 1, you leave this guy alone. You get x, and you differentiate the other guy. And don't expect style points. When you deal with these guys, most of the time, the answer is pretty ugly, and you can't really do anything to make it better. Are you cool with that process? Product rule. Right, I could stick an x cubed there, couldn't I? I could stick an e to the x there, but it'd still be a product rule, and it'd be a very ugly answer, and that's fine, right? You get what you get. Let's try a division. Let's do an inverse cosine of x over the square root of 1 minus x squared. Now, if I want to differentiate that, and I do, I'm going to have to start by writing it like that. Do you see a quotient? So I know its derivative. It's going to be f dash g take away f of g dashed all over g squared. But since this is quite an ugly expression, I'm going to write down the working on the side. There's the f. Its derivative is -1 over the square root of 1 minus x squared. Is that guy done? G is 1 minus x squared to the half. That makes the derivative guy 1/2 1 minus x squared to the -1/2 times something. When you differentiate 1 minus x squared to the power of half, it is a chain rule, agreed? So what have I still to write down here?
-2x.
Correct. And I'll make it a little bit tidier, but not much. You get -x, 1 minus x squared to the -1/2. I'm going to move over here because I need a lot more room than I gave myself. So it's a quotient rule. So it's f dash g take away f of g dashed all over g squared. So it's going to be f dashed, which is this guy, times g, which is this guy, take away the top guy, which is him, times the derivative, g dashed, which is this fella, all over that guy squared, right? This guy here squared. So I'm just going to make my life easy. You know, if you square a square root, you just get that guy. It's okay to do that without writing down the mess. Right, the bottom squared is this guy. Now let's see what we've got here. And actually, I probably should have written that as a square root, shouldn't I? Because that square root cancels out that square root and you just get -1. Two negatives make a plus. And this fella here, when you bring them downstairs and you turn them into a square root, looks like that. And the whole thing is over 1 minus x squared. Oh dear. Style points in this case is necessary. We do not like fractions in fractions, right? We don't like this guy here. What special version of 1 will I use to take care of this guy?
Square root of 1 minus x squared.
And all that does to the bottom, well, I mean, I could leave it like that. I don't think it's that unreasonable. And this guy times this guy gets you negative the square root of 1 minus x squared. And this guy times this guy just gives me an inverse cosine of x. And that is totally acceptable. It's just I'm a picture straightener. And I've just decided this is totally acceptable. Nobody would say that there was a problem with that. This just looks prettier in my brain, not necessarily your brain. All I've basically done is switch places and I've combined them into a single. want to show you something that's really weird. I'm going to differentiate that. That's pretty weird. Would you agree? What on earth is that telling us about the inverse sine of x plus the inverse sine of cosine x when its derivative is 0, no matter who x is? It must be telling me something. So what is it telling us?
Is it similar to the Pythagorean identity where sine squared plus cosine squared is equal to 1?
It's very closely connected to that kind of thing, yeah. What it's saying is that basically, isn't that a number, a constant? Because the only thing that gives you a derivative of 0 is 5 or 10 or 22. So that must mean that the inverse sine of x plus the inverse cosine of x equals a number. I'm just going to call it C for a minute. I'd like to know what that number is. Great. You know, is it 1, you know, like the Pythagorean thing that Robin was talking about, you know, like that kind of sine squared plus cos squared equals 1 kind of thing. So how do I find the missing C if I know that this plus this is always the same number C?
Just like the Pythagorean identity, get 1 to each side?
Okay, I could do the inverse sine of 1. How about, nothing wrong with that. Inverse sine of 1 plus the inverse cosine of 1 should also be C, right? Okay, what angle has the sine of 1? Because that's what inverse sine of 1 means. What angle has a sine of 1?
90 degrees.
Okay, but since we work with radians, we'll call it pi upon 2, but you're right. What angle has a cosine of 1?
Two pi.
And the other
Pi.
alternate would be 0 as well, and I'm picking 0. Which means, so we have created an identity that the inverse sine of an angle plus the inverse cosine of the angle is always pi upon 2. It's not one of those sine squared plus cos squared equals 1 that you're actually going to probably use. But it's kind of cool that you can use calculus to come up with identities that nobody would maybe have ever thought about. I don't think you would have thought that that relationship was true, right? You pick any number you like between -1 and 1, right? And you find the angle that would have a sine equal to that number, and the angle that would have a cosine equal to that number, and those two angles added up always come to 90 degrees. Pi upon 2. A little side issue. Let's do a chain rule. There's the first one. So it's the sine of something. So its derivative is the cosine of something times the derivative of something. And something very strange is happening here. This guy has a little bit, a little bit of style points. What is the cosine of the inverse cosine of x? So you have to think back to 141 and inverse functions and how they interact with each other.
Would it be x?
There it is. That's as good as it's going to get. Let's see if I pick something that they've got, because there's always different ways of doing things. And I don't always think of all of them.
Couldn't you multiply, because that's a multiplication, so it wouldn't be negative x over the square root of 1 minus x squared?
This isn't multiplication. This is inverse functions. This is not a -1 power. This is the inverse cosine function.
Yeah, but the relation between
Yeah.
the cosine and the derivative of cosine, inverse cosine. Right?
Yes,
So it's,
that guy there is -1. Still is. And what I heard is that
is that minus sign a multiplication sign there?
is that minus sign a multiplication. Here is a multiplication. Oh, garden, darn it, and space. Yes, it is. You are right, and I am wrong. That's the answer. I forgot all about that. I guess my brain was thinking separating and wasn't paying attention. Plus, I was too busy thinking of this guy. I want to do the derivative of that very ugly. Okay, somewhere's happened here. There we go. That very ugly chain rule. Okay, derivative of a inverse tan of something is 1 over 1 plus something squared or something squared plus 1. It's the same thing, but I just want to be consistent. It's something squared plus 1. Okay, so 1 over something squared plus 1 times the derivative of that something. I'm doing my usual of writing the thing down when it gets really messy. If you square this guy, you get x minus 2. So that's what that fella is. If I want to differentiate this fella, won't I probably have to call him a fractional power? And so now I have got to multiply, this time I'll remember, multiply a half x minus 2 to the negative a half. Technically it's a chain rule, but times 1 doesn't do anything, so I won't write it. And so this guy becomes x minus 1. This guy here goes there. And this guy here goes downstairs. And then make it look like the original. There's our answer. The derivative of the inverse tan of this square root is 1 over the square root squared plus 1 multiplied by the derivative of the square root. You square that, you get x minus 2, then you add 1. So that's where that came from. If you differentiate this, well, first you turn it into a half power. You get a half, this guy to negative a half. This half generated the 2 that went there. This negative a half eventually gave me that square root. Inverse trig functions tend to generate ugly answers. Occasionally you can make it look a little bit prettier, but the chances are that most of them are going to be just messy and never really recover from that messiness. And now I get a chance to mump and moan for a minute. Have any of you seen arc sine, arc cos, and arc tan? do you know what they are? They're just another name for inverse sine of x, inverse cosine of x, and inverse tan of x. And that -1 is not a power, right? It's just a symbol that represents an inverse function, right? So inverse sine, inverse cosine, inverse tan. So arc tan is this fella, arc cosine is this fella, and arc sine is this fella. So now I can get my mump. Nobody I know, except America, uses arc anybody. It is an old, archaic way of saying these guys. Don't go to a school in Europe. They will look at you like you had been taught by an 80-year-old professor who never changed his ways. They will
Who
say,
says I haven't?
why are you using such stupid old notation? The reason they had these is in the olden days, you couldn't print very easily, if at all, these guys. You know, we have computers now, America. You can do this. You don't need to print things like this anymore. So you and your miles and your pints and your Fahrenheits, get with a program, guys. Get modern. Stop using these bloody things. I refuse to use these. If I see a question with one of these, I am going to turn it into that anyway. So there's my mump. Does anybody here want to get the wrong side of me and defend why arctan is a good idea? Because I'm just going to laugh at you if you do. Okay. I'm sure when I did Teaching 101, one of the things they went and said is, don't threaten to laugh at your students. I'm pretty sure that's high up on the list of things not to do when you teach. Don't threaten your students. I'm pretty sure that's high up. So I managed to do both in the same sentence. So that's pretty good, right?
I have a question. Are you going to mark it wrong on the test if I write it out
No,
like that?
I
Okay,
won't
cool.
be able to, because you'll just complain to my boss and he'll think the arc sign is totally fine as well, because he's an American and he uses feet and pints as well. But just because people do it doesn't make it right. Right? So no, I will not penalize you. But I hope I've embarrassed you and annoyed you enough that you might not use it anyway, just to keep out of trouble, for want of a better word. Are we okay with that? I mean, the stuff we've done, we feel comfortable with it? Okay, for my last version of this question, I'm going to pick the ugliest question I can do. And it's going to be the inverse tan of this. And this guy is going to be ridiculously ugly. And I'm doing it only because it's a homework question. And secondly, I'm doing it to basically show you that you can cope with the derivative of anything. You just have to know how to approach it. So here goes. Its derivative. The inverse tan of something is 1 over the something squared plus 1 multiplied by the derivative of the something. So far, so good. Right. Now, if you square this square root, you get that guy, right? Multiplied by the derivative of this fella, who I'm now going to rewrite like that. So far, so good. Okay, now I'm going to have to do a little side issue, and I want to take care of the side issues as they happen. Part of our answer looks like this. You know we don't like fractions with fractions in it, and there are going to be a lot of style points in this question. So the way I'm going to fix it is by multiplying by the special version of 1 minus x. So the top becomes 1 minus x. And this guy times this guy is 1 plus x. And this guy times this guy is plus 1 lots of 1 minus x. And this becomes 1 minus x. And almost like magic, this guy becomes 2. And that can be written like that. Was that a surprise? You agree? That was kind of surprisingly nice. Right. Next side issue. I need to find the derivative of this ugly guy. Well, he's something to the power of half, so he's a general. He's 1/2 something to the power of negative a half times the derivative of that something. So it's going to be times 1/2 1 plus x 1 minus x to negative a half times the derivative. Actually, I shouldn't need to have bothered that, but let's go on. Okay, I need to figure out this fella now. Won't that be a quotient rule? Can you see why this is like the question from hell? I mean, it has got the whole package in it, right? It's got chain rules inside chain rules with weird fractional powers, quotient rules, who knows what else it's going to have. The top's an F and the bottom's a J. So let me do this guy. F dash J, take away F of G dashed, all over G squared. That guy's derivative is 1. Leave this alone. Take away, leave the top alone. Derivative of that bottom guy is what? -1 over this guy squared. So I have 1 take away x plus a 1 plus an x over 1 minus x squared. They cancel out, and it's actually quite nice. I'll write it down again. It's that guy. So what do I have? I have a half, 1 minus x. I got another a half, so I guess I should turn it into a quarter. I got this fella, who I'm now going to call that guy. And we got this fella, who's now going to be called that guy. Can you see this negative a half power has now been turned into a positive a half power? You see this? 1 plus x over 1 minus x to the negative a half has been rewritten as 1 minus x over 1 plus x to the plus a half. Okay. This 2 cancels with that and leaves me with a half. That's good. I have a 1 minus x. I have a 1 minus x to the half. I have a 1 plus x to the half. I have a 2. And I have a 1 minus x squared. Now, any kind of cancel. Sorry.
What did you get the half? How did you get the 1/2 from 1/4?
quarter times this 2 became a half. So this 1/4 and this 2 became the half.
But and that doesn't
That doesn't make the 2 1.
Doesn't make the 2. Oh, God. Thank you. Yeah, I now know what you're getting at, Zoe and Robin. Okay, let's make, well, let's do some killing. That's 1, and that's a half. So isn't that 1.5 powers? Won't it cancel with this and leave a half power? So what do I have? I have a half. I have a 1 plus x to the half. And 1.5 and that guy leaves me with a half power on the bottom. And that is going to become 1 over 2 times the square root of 1 plus x, 1 minus x, which I kind of like, or 1/2, 1 over 2, the square root of 1 minus x squared. I mean, considering what that was made up of, isn't that a remarkably simple final answer? But there's a heck of a lot of fractional powers cancelling out. These guys cancel out most of that one and leaves this behind. And it's the right answer because I'm looking at it right now. Any questions about this before we move on? Inverse trig functions. Product rule, quotient rule, chain rule, right? Same rules that you get with everybody else. So we're now going to start our next section. And it's rates of change. Right now, we've been finding derivatives more like an algebraic exercise, right? Or a geometric exercise. Here's a curve. What would the slope of the tangent line be? And that's all well and good. It does what it does. But let's actually try and look at derivatives from the perspective of a concept called rates of change. If I said to you, I'm trying to remember which way around you do your deltas. You do your deltas the other way, don't you? Do them that way? Which way do your deltas? This way or that way?
pointing up.
Okay. These are deltas as well, but they're calc 4 deltas, so I won't go into that. Right, if I said to you, the change in distance divided by the change in time, you might call that speed. It would be better to call it velocity. And that's an example of a rate of change. It's a rate of change in position with time. Very often rates of change is respect to time, right? Time is changing and what's happening to something. So you could have the rate of change of temperature with time, the rate of change of position with time. You could have the rate of change of velocity with time. What do you call the rate of change of velocity with time? Because it has a name in physics and mechanics and
Acceleration.
whatever. It's called acceleration. Well, wouldn't it be nice then if calculus could help us to find velocities and accelerations, for instance? Let's say, assume that I have a formula for the height of an object at time t. And this formula is 2 plus 5t minus 16t squared. So can you imagine I did a little sketch of this? It would probably look something like that. So it would be the height at any given point t, and that would be quite natural. Can you imagine you threw some object in the air, right? And you were what, 2 meters off the ground when you did it, right? Because that's your height. It would have this kind of quadratic shape to it, wouldn't it? And this formula would tell me the height. I would like to know what the velocity, right? The instantaneous velocity of this ball at any given point. Well, if you want to get velocity, we'll call it v of t, you just find the derivative of that guy. So the derivative of position, the rate of change of position with time, gets you velocity. So we can think of derivatives as just a rate of change. In this case, the rate of change of height. And if you do this guy, you get what? 5 take away 32t. So if I wanted to know, for instance, what's the velocity of this object after 1 second? You would be getting the answer, negative 27 meters per second. And if you've done classes involving, is it kinematics? I'm trying to think of the class that you do moving objects in. Right, if you did a class in kinematics, you should be comfortable with the fact that velocities can be negative as well as positive. In the concept of this picture, wouldn't a positive velocity mean that it was moving upwards vertically? And a negative one means it's moving downwards. So that might mean that after 1 second, that's where the ball is, right? And it's heading towards the ground. So the key to what we're talking about here is, let's do it as a general one. If I give you the position of a moving object, if you find its first derivative, you will now have the velocity of that object at any given time. What do you think you get if you differentiate the velocity function? So what's the rate of change of velocity with time?
The acceleration.
You have your acceleration. And if you only think in multiple derivatives, then is it the first derivative velocity and the second derivative acceleration? And you could keep going that. Can I do the third derivative? And the fourth and the 24th if I wanted to. And I have been told, and I know it's true because I did look it up just to make sure it wasn't true. There's actually a name for the rate of change of acceleration. Does anybody know that name? Because you may have heard it. And it's, trust me, look it up when this is finished. It's called the jerk, J-E-R-K. Now, evidently, it's not that common a thing to want to do, but you can find the third derivative. And the student who told me about it, and I did check it, that it does exist. If you're in a moving object and you've got a constant acceleration, you don't really feel it much. I mean, you feel the car getting faster, but it's not a sudden change. But if you have a moving object where the acceleration itself is changing through time, then if you were in a car or a spaceship, you would feel a kind of jerk forward. And that's probably where it got its name from. So first and second derivatives are very common. First derivative gets you velocity, second derivative gets you acceleration. So you can find any kind of information you want from a moving object by only knowing this. Where is the object, right? Just tell me its position at any given time t. Now, I'm pretty sure they do this in NASA, but in a much more sophisticated three-dimensional way, which you'll learn when you do Calc 3, because it's three-dimensional movement, not two. But I'm sure in NASA, they find asteroids all the time. But what they do is that when they see an asteroid, they record its position over a number of different points in time. And then you can plug it into a computer and you can say to the computer, make a curve that fits that movement. In other words, you create this formula. But once you've created this formula, can't you then find the velocity of this asteroid and its acceleration? And so not only will you know where that asteroid is going, hopefully if you do it well enough, you will, and you'll also be able to say it's going at 10,000 miles an hour and it's accelerating at this rate or whatever, right? You can find out pretty much everything you need to know by only knowing its position at a given set of time. It's pretty powerful. And that's why they have, have you ever had those ones from time to time? Oh, there's going to be an asteroid that's going to get really near to the Earth. And it all sort of worried me until, do you know what they call near? Anything that's between the sun and us, that's near. And then when you look at how big between us and them is near. Now, what do they call dangerous? Anything that's between the moon and us. And do you know that's, what's that, 250,000 miles, I think? Right. So an asteroid the size of a bus has got 250,000 miles to miss us. It doesn't seem that dangerous anymore when you think of it in terms. So I think they guys just get fun by, let's freak out everybody and tell them about this asteroid that's going to be very near to the Earth this coming Tuesday. Now, if I was in charge of NASA, I would give asteroids scary names. I would say this Tuesday, the asteroid, the Deathbringer, is going to be in a near orbit to the Earth. Wouldn't that get people panicking? Wouldn't that be a cool thing to do? Because you could go home and know there's not a chance in heck of it ever hitting anything, right? But everybody else is trying to figure out where in the Earth you should be if an asteroid hits. And the answer is anywhere you like, because the asteroid can hit anywhere. Right. So the best place to be when an asteroid is going to hit the Earth is in your house, in my opinion. Okay, before I forget, and I know I'm running over a little bit of time and I do apologize because your time is important. So why don't you say hi while I get this thing set up for you? There is something I need to explain once I get this darn thing moving. I think I'm running. Where are you? There we go. Gotcha. Gotcha. And now I can show you. So make sure you said hi. Right, you should be looking at our screen right now. And let's put it on student view so it looks more like what you would say. Right, are you looking at our class Canvas site? Right, you may have noticed there's a 2% extra credit. So if you do this, and it's totally up to you, you can choose to or not, but I very strongly suggest you do it for two reasons. One is 2% is nothing to be scoffed at, especially if you would end up with a 1.8 at the end of this class. You're going to be kicking your butt saying, I wish I'd done this. If you go inside, let's tell you what it is. I have a video that I created for one of our sections, and it's actually the section, I think it's 310, and it's on linear approximation and differentials. And you will watch this video instead of Friday's lecture, because I will not be here on Friday, or at least I won't be, well, I will be on the Earth. It's not that bad, but I won't be doing my usual thing. And inside this video, there are 5 questions. And when you get those questions, you will hit new attempt and you will type in the answer, hopefully. Well, it depends what the answer is. The answer might be a linear equation, like y equals, well, it's a linear approximation equation. So it'll be something like that. And you will tell me which one it's the answer to. I guess doing something like this. Right. Or you might be doing one of your answers. I know you might be doing it, like maybe question 4. Your answer might look something like this. It's a differential. And you have to do that. So it's not the prettiest way of doing it, but you can play about with it. There's some, for those who feel brave, can you see you can type in all the math symbols, but it's not everybody wants to know wants to learn how to use that. So your backup plan is just type it like that. But if you want to be prettier, you can do that. Now there are 5 questions and it's a 2% extra credit, and you can have as many shots as you like. And I only need to see the answer to each question, so you can do the work in scratch paper and just tell me the answer. Some of your answers are going to be numbers like 1.234. And does that make sense? Right. You have got until Sunday midnight to get this done, so you don't need to do it on Friday. But it probably would be a good idea just to be in the habit to turn up on Friday, right? And just do it, watch the video, just like you were taking a class. And bye-bye. I think I've kept you enough.